Thanks, everyone. Welcome back after the break. So my name is Mehak. I work in the software engineering for Broadcom's networking team. And I have the privilege of presenting with Guohan Liu, who is from the software engineering from Microsoft Azure team and driving the development and deployment of Azure data centers. So today we're going to talk about the technologies that are being used to enable the large-scale backend AI clusters. And to start off with, we'll just discuss about what makes these data centers different. So the AI traffic characteristics, followed by a deeper dive into the Microsoft Fairwater data centers and the technologies that are getting actively deployed in this to enable the large scale that is present in the Fairwater. And lastly, we'll just leave you with some food for thought for what's coming up for the newer features as they will start coming into the SONiC community. So before we start, let's just take a step back to think about traditional networks. Traditional networks were designed keeping in mind several small independent transactions that were bouncing between web servers, databases, etc. And the network for that, even though it's chaotic, is quite forgiving. That means the randomness in the network gives the network a chance to breathe. The congestion slowly starts creeping up, but since these flows are spread out, the network recovers as well. AI data centers turn this model on their head. And the AI data centers are mostly comprised of several long-lived but synchronized flows, which we call as elephant flows. These flows have almost no entropy or variance in them. So several thousands of GPUs finish their compute step and start transferring data across the entire AI fabric simultaneously. Having no entropy, these end up following the same path at the same time. So this leads to bursty traffic and leading to short-lived spikes in network congestion. And in this case, the traditionally designed PFC ECN does not really help you much because this was designed for gradual congestion and not for bursty traffic. In fact, if the buffer sizing for PFC is not done right, it can lead to head-of-line blocking and congestion spreading. And let's talk about telemetry. In the older times, which was not very long ago, the telemetry would be pulled from the ASICs in many seconds intervals. But since these are short-lived spikes, you need to have telemetry that is real-time, and you need to have feedback or fast feedback from the network as well. You need to know what is the buffer occupancy and link utilization so that you can mitigate congestion before it starts to impact your network performance. And lastly, the AI network performance is not defined by averages. It is defined by the slowest packet in the network. This means when thousands of your GPUs are waiting for that one straggler to complete, even the slightest increase in latency quickly adds up and increases your overall JCT. So my friends, AI networks is not just a scale problem. AI workloads are not just bigger, they are different. So any network that has been designed for AI must take care of bursty traffic, real-time network insights, and fast feedback from the network. Now Guohan will walk you through the Fairwater data center that has been designed with Tomahawk 5 Broadcom ASICs with precisely these design points.
So as you may know that Microsoft has built the largest AI data center in the world. So when we try to build this network, so one of the key things is to really build a very highly scalable network that can connect to hundreds of thousands of GPUs together without degrading any performance. So the way that we look at it is to really leverage the ASIC capabilities to build such flat and wide network. So usually can go to the next slide. Yes. So what we're doing that we build a two-layer, leaf and spine network. However, we leverage the radix of the latest ASIC to scale the ports as many as possible. So in this case, you can imagine that this 51 terabit ASIC has 512 links. And traditionally, usually the ASIC does not have 512 max. So this was a problem. So in our case, we work with ASIC suppliers to make sure that not only they have 512 links, but they also have 512 max, which means that each link will become a physical link that have max and carry traffic. And we can leverage that to build a very large and flat network. And so the key requirements here, for example, in this case, we build a multi-plan, multi-rail network, where in each plan we could have maximum, 256 T1 and 512 T0s. Imagine this ASIC have 512 links. So on the T1, each link is 100 gig and connect to each of the T0. And on the T0, it have 256 uplinks that connect to each of the T1. And on the downlink side, it connect to 256 NICs. So in this case, if you calculate the total number, that would be 524K GPUs. That's a maximum scale that we can build by leveraging the key feature from the ASIC, 512 max ASICs, to build such flat network, and a very cost efficient and low power. So once we build such large network, as Mehak described, that we have so many challenges in terms of elephant flow, in terms of congestion control, and in terms of telemetry. So I'm going to talk about the two key technologies where we enable on the software to be able to scale for such large network. One is the BGP, another is SRv6. And I think Mehak will talk about the packet trimming and high-frequency streaming telemetry. Okay, so yes, we did build this large flat network, and now you can imagine traditionally, you talk about a 64-port switch, and the largest scale you have the BGP is 64 BGP sessions. But now imagine you have 64 ports, and each port break into 8 ports. You have 64 times 8 links, and each link is running a BGP session, and suddenly you will have 512 BGP sessions running a single box. Usually, you do not run such high-scale BGP sessions on such a pizza box. You, of course, run it on chassis, but the chassis is a very different system. And in this case, we have to, in order to make this work, we have to make, this 512 BGP session work. And, during the past, 9 to 12 months, Microsoft worked with communities and spent a lot of efforts to really scale the software stack in order to meet these challenges. So what we have done, it's all in the open source now. We have working with the community to do the FR upgrade and to the 10.0.1, and even with that upgrade, we worked out 20 patches related to various things. For example, the limitation of the next hop numbers. There's a timer issues. So roughly about 20 patches that we have worked together with the community to make the BGP scale work. And now with this new FR and this 20 patches, we are able to support 14 BGP sessions and next hops. And So with such numbers, 512 BGP sessions and 1K routes and 512 next hops, now we are able to bring up, from the box from the start, all the links go first initially down, and then bring all the links up, and then all the BGP sessions start simultaneously. We are able to achieve, the convergence time within, 100 to 150 seconds. I mean, even though this is not, what we want to get there, but it's a huge step compared with what has been done in previously. So we're going to continuously improve on that. But for some other key metrics, right? So for example, if there's single link flaps and the data plan down during that link flap, we're able to achieve sub-seconds and the sub-10 seconds convergence time, which is great. And so once we solve the BGP session issues, and then we are able to basically provide the basic connectivities for the network. Then the next one is that, as Mehak mentioned, all the AI traffic are elephant traffic, and there's a little entropy on that. So in order to really, achieve a perfect load balancing in the network, what we end up doing is that we give the control to the NIC, to the host, where they have perfect knowledge of how a collective is running, and what is the traffic pattern for that collective, and what is the destination and the source destination pairs. So they know everything about the traffic demands. So then they can create a perfect traffic scheduler to schedule those traffic and avoid any collision on those single links. And imagine those links are no longer we're talking about 800 gig links, we're actually talking about 100 gig links, right? So it's a very thin, schemy link. So in this case, what we're doing is that, in the network, we provide the capability for the host to do the source routing. And what we're doing is that we're adopting this well-known IEEE standard called SRv6 to enable that source routing in the network. So, and so basically, we in the SRv6 there is a microset concept where each microset is only occupy 16 bits in the SRv6 destination header, and when the source NIC send the traffic, it knows which path it wants to take, and they know all the seed allocation on each switches, so they can pre-allocate the seed labels, the stack of the seed labels, and put in on the SRv6 header, and then send the packet with the SRv6 header. And then once the packet reaches to the Tor, it will be hop by hop and be source routed to the destination. In this case, the NIC has total control of the path and can completely avoid any congestion happen during the, during the network. And so, there are some details. In this case, if we're doing, pure IPv6 header without SRH, we can accommodate up to 6 USIT, meaning you can do 6 hops. But if the network is bigger, we can add an additional SRH header to enable more hops to be source routed. And the switch are the SRv6 transit switch, meaning only process the UCIT stack and then drop the packet if the stack doesn't match. So the strict source routing is enabled on the network. And once the packet reaches to the target NIC, it will be decapsulated and send the original packet back to the host. And so, as a variant, we support both UA and UA. UA is still in progress, but we're going to also support the UA for this network.
Thank you. So one other feature that has been enabled for the network is the packet trimming feature. So in the beginning, we said AI traffic is bursty, and we want the jobs to complete really quickly. So this actually leads to kind of a tricky situation where you don't want to stall the network, but you still don't want to drop the packets. Historically, in order to accomplish a lossless network, you've enabled PFC. But as I mentioned, PFC can quickly spread if you breach the thresholds associated or configured for PFC. And you can spread the congestion, thereby bringing the network to a grinding halt. So PFC, while can be used, you need to be very careful about how you size these buffers. But since you don't have control over the network traffic, you may still have bursts that will assert the PFC. So what do you do in something like this? This is how the traditional networks operate. In a newer network of AI, you want the network to start providing feedback and very quickly so that the packets, if at all dropped, can be retransmitted well within time so that the average job completion time does not increase. In order to do that, you can have a feature called trimming, which means that if the packet were to get dropped, you trim it and send an indication to the endpoints to retransmit. So how does trimming work in the AI backend? You start off by classifying the packets or the traffic that you want to be trim enabled. This could be done on the basis of a DHCP code point, which is used to identify all AI traffic. If at all the congestion is experienced and the packet is getting dropped, the dropped packet is trimmed to a small size and is quickly forwarded over a high priority queue to the destination NIC. The destination NIC obviously needs to be trimmed, needs to be able to react to trimming, so that functionality needs to be available in your end NICs. And it will react to this trim by sending a NAC back to the source NIC, letting it know that this packet has been dropped owing to congestion in the network. The source NIC will then retransmit the dropped packet, and that will be fast-tracked over the network to reach the destination NIC at approximately the same time. Of course, in this process, depending upon the amount of trims or NACs that you are getting, is also an indirect indication that the network is highly congested. And so if the NICs are capable of doing end-to-end flow control, then it will automatically reduce the speed at which the packets are getting retransmitted, thereby allowing the network once again to breathe and for the congestion to subside. Now, as I said, in case of trimming, the packet is trimmed and sent forward. This leads to a natural compression of sorts in the network and can handle incast to a certain extent, depending upon how small you trim the packet to. But obviously, you don't have control over how much incast is going to be there in the network. And so if your switch is capable of having a dedicated trim buffer, then you can allocate that dedicated trim buffer in order to absorb even higher incast ratios. And that way, you can end up absorbing more of the incast. Lastly, we spoke about telemetry and how the traditional telemetry just doesn't cut it. As Guohan mentioned, obviously, one of the challenges that was associated with scaling the switch to a high radix of 512 was the fact that BGP sessions had to be scaled. But note that as the ports go up, your telemetry challenges just become a nightmare because you no longer have to collect ports from just a handful of 32, 64 ports. You have to start collecting this particular telemetry or counters across 512 ports, which is 4x or 8x more amount of telemetry that has to be collected, but at a much shorter cadence. Because if you recall, we said the traffic is bursty and the congestion is short-lived. If you lose the window in which this congestion has happened, you will not be able to figure out where and how the packet got dropped. So because of this, we have changed the paradigm in which how telemetry needs to be collected. Rather than having the NOS go and query the ports or query the ASIC for all the telemetry, the ASIC will now start a push model or will push all the telemetry that it is capable of pushing through the Linux stack to the NOS. This updates will come to the countersync D in a specific format. And this format, which we have picked from in the SONiC community, is the IP format. And predefined templates would already have been programmed in the SONiC NOS. With this, as the message comes, you see if it is one of the existing templates. If it is, you process the packet. You can either store the telemetry locally or convert it into an open telemetry message and send it off for an offline processing. So all of these features, as Guohan said, are already deployed and actively getting rolled out into the Fairwater data center that is getting deployed with the Tomahawk 5 switches. But these are all available, and detailed HLDs are available in the SONiC community for you to take a look at. The SRv6 UCID HLDs, the packet trimming HLD, and the high frequency streaming telemetry HLD. So what's next? Right now, all the features that we described are catering to a scale-out network. Right? Packet trimming, well, high-frequency telemetry can be applicable for others as well. SRv6, because this is multi-hop, it is all for scale-up network. However, we all know that there is one more network which is very crucial to AI backends, and that is the scale-up network. A scale-up network is a high throughput, low latency, lossless, resilient network that is needed for GPUs to quickly communicate to each other. And this week, you heard the OCP announce a work stream in which 12 companies, including Broadcom and Microsoft, are coming together to start defining the set of features that will be used to define a good Ethernet-based scale-up network. Keeping the specification on its own, the 1.0 has already been published, and you can take a look at it. But what it aims to do is that it aims to separate the network layers from the GPU layers, allowing the GPU interoperability, allowing the GPUs to innovate in their own space on the transport layer. But since the L2, L3 framing would be the common Ethernet framing, it will actually allow you to send packets effectively over the scale-up network. And you don't need to reinvent the wheel. So keeping this in mind, the SONiC community had introduced the scale-up work group and is being driven by Eddie from Alibaba and Guohan from Microsoft as chairs. And the specification is already starting to shape up. Many of the good features that you will read that you will hear about are already in the scale-up work group's initial draft, like LLR, CBFC, flex headers, and others. And I invite all of you to attend Eddie's and Riff's session later on, where they'll give you the state of the union for what is being done in the scale-up SONiC work group. Lastly, we are an open community. We invite contributions from all of you. We would like to see all of you participating in the SONiC community, and these are just some of the resources that will help you start participating. And please come and talk to us if you have any questions about how you can contribute to the SONiC community to make the SONiC code address even more use cases than it already is. Thank you.
Yeah, all these features are open, available. Use it and get feedback. Will make the SONiC better for the scale up and scale out network.
All right, we do have a few minutes. Any questions for the speakers here?
Thanks, Guohan and Mehak. That was a great presentation. I have a question about one of the comments that you had around the microSID. When you said that if the microSID is not available on the switch, then you drop the packet. Do you send any notification back to the source NIC when that happens?
Oh, yeah, that's like a black hole job in this case. I think no, I think we're expecting that is treated as a typical job, right? So because this is, the routing is wrong, so there's something wrong, you cannot route the packet to the destination. So you treat it job, and the host will do the retransmit.
Okay, thank you.
Hi, thank you for sharing the info. Sorry if I missed, but what is the background of using the 100 gig for uplink rather than using 800 gig?
Oh, why do we break to those 100 gig link?
For uplink?
Oh yeah, because we want to do the multi-plan. That's way to scale the number of GPUs that we could possibly end up, 500K GPUs in one DC.
Oh, okay. So yeah. you want to increase number of the layer?
Yeah, we are building the largest DC, AI DC in the world.
Oh, I see. Thank you.
Thank you for the presentation. I'm Jonathan from Esther Labs. I have two questions. One is for the telemetry update. Does it involve change to the SAI definition? Second question is, how does it send the streaming data out from the switch platform? Is it using gRPC?
So for the size specification, yes, it did require changes to the size specification in order for you to communicate some of the information down. That specification is already a part of the latest size specification that has been released.
What version is it?
It's I think 1.16.4 already has the telemetry, SAI telemetry specification as a part of it. We are about to release 1.17. So the one previous to this already has SAI information as a part of it. And in order to send the data out, yes, we are using gRPC.
Okay, thank you.
Thank you. Thank you.
Thank you again.